Hi, in this video, we're going to take a look at singular value decomposition and principal component analysis. All right, so singular value decomposition is a factorization, a decomposition that all matrices have. On the left-hand side of our decomposition, we're going to have a unitary matrix. The dimensions of that unitary matrix are going to be equal to the rows of the decomposed matrix. And on the right-hand side, we're going to have the transpose or the adjoint of a unitary matrix that whose dimensions will match the number of columns of the decomposed matrix. Now, we've got unitary on the left, unitary on the right. Well, those preserve geometries because they're unitary. What is really neat about this is that in the middle is we're going to have a rectangular diagonal matrix that the diagonal entries are going to correspond to our concept of like a higher, more general version, a higher dimensional version of variance or standard deviation, depending on how you want to look at it. All right, so here, singular value decomposition is a fundamental matrix decomposition technique that provides a structured factorization of a matrix. All right, so here we're going to say that A is our matrix. Usually A is going to be for us a data matrix. Okay, and so now when I say a matrix, all entries are going to be from either the real numbers or possibly a more abstract algebra situation of a field. But most of the time, overwhelmingly, everything's just going to be, it's a table of numbers. A matrix is a table of numbers. And we have m rows and n columns. Okay. Now, in my decomposition, I have A is equal to U times diagonal sigma times the transpose of unitary V. All right. U is going to be m by m. Notice that A has m rows. V is going to be n by n, unitary. And then the sigma is going to be m by n and diagonal, meaning that all entries that have the row and the column are not equal to each other are going to end up equaling 0. Okay. Well, in this situation, U and V are unitary. Those are going to be preserving the geometry of whatever they're going to preserve the distances between things that we multiply by the matrix. And so that means that all the variation that's going on in A has to be accounted for by that middle part, the sigma. All right, so that sigma is going to give us our higher dimensional version of standard deviation. All right, so U is m by n, unitary matrix. Sigma is diagonal, m by n. And we're going to go a step further with our diagonal aspect, and we're going to say that we have a descending order. We have the largest in the upper left-hand corner, and we're going to, as we go down the diagonal, the sigmas are going to decrease. All right. Now, this P here, this is going to be the minimum of M and N. All right. So let's go ahead and pull up some data. Now, in data science, we almost always want to rescale our data before we start writing principal component analysis. There are times that you don't want to. Here, I'm going to assume that we want to for what we're working on. Composition data, we would actually be doing our centering in a different manner. We would be dividing by the geometric mean instead of subtracting by the column mean. So that's for composition data. And if my data is already on a consistent scale, maybe not exactly the same mean or not exactly the same standard deviation, but things are on the same scale, let's say like, 1 to 5 star or something like that, I might not want to center and scale my data. Most of the time we're going to, so I'm going to go ahead and do that here. I'm going to work with the US arrest data set. All right, and here I'm just going to rescale it. So each column has, after I scale it, each column has a mean of 0, standard deviation of 1. And now let's go ahead and take this singular value decomposition. Now, to make it easier for you to spot the connection between the original data and the singular value decomposition, I'm going to go ahead and start tacking on some names onto what's going on. All right, so here, the U, I'm going to match up the row names here. So the row names of U are going to match the row names of the original data set. The column names of U are going to correspond to the components. Notice I've got U right there and U. Yeah, so the main part, column names are going to match components. And now for those standard deviations, the diagonals, we're going to match those up to the components. And for V, we're going to match up with the column names of the original data and with the components. So you'll notice that the rows match up with the column names of the original data, the rows of the columns of the original data, and the columns of V match up with the components that we're going to get. All right, so now let's take a look. All right, so sigma is a diagonal matrix with these values. So here we have 50 states. So the actual sigma matrix is going to be a 50 by 4 diagonal matrix. All right, so 50 by 4, the only time we have a non-zero entry is when the row number equals the column number. And so that means that we are going to have 46 columns of all zeros. And on the far left, we're going to have like a diagonal submatrix. And so now we can scroll down and we can see the connection between the original data rows and the components when I get to principal component analysis in a moment. Scrolling down here. Now here's V. V is going to correspond to the loadings, and that's how we're going to interpret our latent variable analysis using exploratory models with principal component analysis. And so here, see that the rows of V correspond to the columns of the original data, and the columns of V correspond to the components. One thing to remember, though, in the formula of the multiplication is that V is not in the decomposition, it's transposes. So it's not, there is a difference there. We just need to keep it straight when we look at this formula. All right, so now I want to show you that this decomposition actually equals the original data. So if I take the U, the D, and the V, and I do the matrix multiplication, I will get the original data up to rounding off due to machine inaccuracy. So here I'm taking the U part of the SVD. I am taking the diagonals here. Notice I'm making a diagonal matrix. I'm taking the V here. Now I'm going to take the original data. Remember, I rescaled it before I did SVD. And then I'm going to do the matrix multiplication. And here I'm going through and I'm computing the Frobenius norm of the difference between them. Boom, look at that. Now, it's not perfectly accurate. That's because of inaccuracies due to rounding off within the machine. But pencil and paper theory is perfectly accurate. All right, now to show you entry by entry, if I take the original data minus the multiplication, so I'm subtracting off the multiplication, you can see that I've got all zeros after I do the subtraction. All right, so let's talk about properties and interpretations. The singular values measure the importance of each singular vector pair. All right, so something about that, since I put things from largest to smallest, this statement tells us that the most important singular value vectors are the first ones. And the eigenvalues of the transpose of our matrix times itself and the matrix times its transpose are first of all, they're going to be square. And the eigenvalues that we get from these are going to be the squared singular values that we just saw a moment ago. So if I take those D values, the values from sigma, those squared are going to equal the eigenvalues from here. Okay. Now, one of these two, if A is not a square matrix, one of these two is going to have zeros for eigenvalues. They might both have zeros for eigenvalues. But so all the ones that are eigenvalues of the one with lower dimension, all those eigenvalues will be in the other one also, but the other one will have a whole bunch of zeros in there. Typically, when we have a data matrix, most of the time we have more rows than we have columns. And most of the time, from a theory point of view, we make the assumption that we have full rank, meaning that the number of non-zero singular values that we're going to have is equal to the number of columns for typical data science use. All right. The rank of these two products will always be equal to each other. So the rank is the number of like distinct dimensions in linear algebra for the span of it. Most data matrices have more rows than columns. And when there are more rows than columns, A transpose A will have a lower difference between its rank and the dimension. When there are more rows and columns, the dimension of A transpose A and the difference with rank is going to be less than the corresponding ATA. Okay, so what I'm going to do, this since this is not as well written as it could have been, what I'm trying to say here is that rank of our original data is going to be closer to the dimensions of this matrix than the other when we have most typical data situations. And when I have full rank in my data, meaning I have zero collinearity aspects, then there's going to be perfect equality of the two. All right, so what I'm going to do, I'm going to refer to A transpose A as the full rank product, and I'm going to refer to A transpose as the low rank product. Now, this may not actually be full rank, but it's the, like, I should say maximum rank would be a better wording. All right, so let's take a look at this. All right, so I'm going to compute the eigenvalues of the transpose times the original data. Now, this is a symmetric matrix, so I can speed up the process and improve numerical stability by specifying that this is a symmetric matrix. All right, so now here I've got my eigenvalues here. And if I take the square root of the eigenvalues, you'll notice I get the same values for the singular value decomposition. These are the same. All right, well, let's keep it going. If I look at the vectors, the eigenvectors from A transpose A, I look here and I see that they're nearly the same. All right, if I multiply this one, no, column 2 by -1, you'll notice that I get column 2 of V. So the first one here is equal to the first one here. The second one, if I multiply by -1, then I get the same thing. If I multiply 3 by -1, I get the loading here. And this is equal to that. All right, so when I'm doing principal component analysis and when I'm working with eigenvectors, if I unitary matrices in general, if I multiply an entire vector by -1, it's not going to change the result from like a theoretical perspective. Now, the interpretation might be in the opposite direction, but it's going to end up being like the same, conceptually the same thing. Just everything's going to be reflected. All right, now if I take the low rank product So here I'm taking A times its transpose. Now here you can see that I have exactly the same eigenvalues I had before, but then I have a whole bunch of zeros. So here, that's a little, so the square root of this is a little bit more than 11. And boom, look at that. It's the exact same value. All right, another use of singular value decomposition is that we can get something called a pseudo inverse. This is a generalization of the inverse of a matrix. So what I'm going to do, I'm going to take my singular value decomposition. I'm going to reverse the order. I put V on the left without a transpose. I put U on the right with a transpose. I'm reversing this, effectively I've taken the transpose of everything and switched it around. Now, for sigma plus, though, what I'm going to do, instead of having those singular values, I'm going to have one over the singular values when they're non-zero. If it's zero, I just leave it alone. And this is a generalization of a regular matrix inverse to rectangular matrices. And so we're going to be using singular value decomposition for dimension reduction, principal component analysis, and solving linear systems and computing pseudo inverses. It's used all over the place. All right, so let's go ahead and use singular value decomposition. So let's talk about estimating singular value decomposition. Um, so if I'm going to be doing if I'm going to be working with actual data, I'm more than likely going to want to mean center my data. Mean centering my data is going to be important for this because of some calculations we're going to do in a moment. I most of the time I say you need to actually center and scale, not just center, but centering is more important for this. Um, this is just basically a repeat of what I've already said. Now, the variance explained by each component is going to be the square of those standard deviations from SVD divided by n minus 1. And in dimensionality reduction, I can use the proportion of variance to address how much variance is accounted for by my using my components in like a dimension reduction situation. All right, so the first principal component always captures the highest variance, and each subsequent component is orthogonal to the previous ones and captures the next highest variance. Okay, so subsequent components are orthogonal because of that unitary matrix aspect that I told you about earlier, that U business going on. And subsequent components capture the next highest variance because of the ordering that we have of the singular values on that diagonal. All right, so let's go ahead and compute principal component analysis on our data set. So notice I'm taking the scaled data, and base R has two functions that you can use, prcomp and printcomp. All right, the help documentation indicates that prcomp is more stable numerically, but printcomp honestly has more functions that interact with the output to, support our projects. And so if you don't have a problem with numeric stability, you probably want to use a printcomp. All right, with center and scale data, our low rank eigenvectors correspond to principal components. Now, to show that, what I'm going to do, I'm going to take my eigenvectors and I'm going to take our principal component analysis scores, and I'm going to take the correlation. And you'll see, boom, I have perfect correlation, but you'll notice I have plus or minus 1 because of that whole -1 multiplication doesn't change our components. Now I'm doing exactly the same thing, but this time I'm doing it with the PrinComp version of PCA. And you'll notice once again, perfect correlation up to the sign. All right, if I look at my full rank matrix eigenvectors, and then I look at my loadings, all right, notice that here I've got, these are all negative. In column one, these are all negative, but I've got the same values going down just if I multiply by a -1. Here, I've got the same values in 2 as comp 2, same values in 3 as comp 3, same values in 4 as comp 4, up to rounding. Oh, the print function automatically drops values that are close to zero below a certain threshold to help us make it easier to interpret the loadings. So that's why it's not appearing here. Now, the loadings is what's called with print comp. With PR comp, it's called rotations, but it's going to be the same values anyway, up to a negative sign. If you just go through, you'll see exactly the same phenomenon of all 4 columns. Okay, so we can also estimate our principal component analysis, scores, loadings, rotation, whatnot, using a covariance matrix. All right, so if I take my variance covariance matrix, which I can compute by taking the transpose of my data times my data matrix. This is after I do mean, I center by the mean, but I don't rescale, then divide by n-1, I'll have the standard variance covariance matrix. All right, well, it's going to work out that if I do the matrix multiplication of my singular value decomposition that I would get from Z, it's going to end up that I've got with a data matrix, the smaller matrix and its transpose is on the left and right of a diagonal matrix with the variances going down the diagonal. Okay, and so it's a symmetric matrix. That means it's super easy to decompose. We know that it's unitarily diagonalizable, which we can see actually on the page right now. And so what this does for me is once I get my variance covariance matrix, if I take its eigenvalue decomposition, then I'm going to get that V matrix that we saw earlier, and I'm going to get the squared version of D automatically. So now I've got most of the components of my singular value decomposition from the variance covariance matrix. Now, there are multiple ways to compute this. The matrix algebra, I find it really interesting, but I don't want to go any deeper than this on this point. Now, if I want robust principal component analysis, an option that I have is to, instead of using standard variance covariance matrix estimates, I can use a robust version and then go through this process that I have right here. If I do that, then I can use that to get a robust estimate of principal component analysis. All right. And so just to show you this, here's my variance covariance matrix. And here is me taking my centered data transpose times itself, centered data, divided by number of observations minus 1. And you'll notice I get exactly the same matrix. Now, you'll notice I've got 1 on the diagonal because I scaled my data to have variance 1 in each column. The eigenvectors from the variance matrix gives us the loadings / rotations of our principal component analysis, which are the same values we saw earlier. And you'll notice that if I take the eigenvalues from the variance matrix, that's equal to the square of the standard deviations. And here are the loadings from principal component analysis. And here are the vectors from the covariance matrix. And you'll notice up to a negative sign, everything agrees. All right, so now here I'm going to demonstrate the one robust version of principal component analysis. I looked through a couple of different packages on robust principal component analysis. This was only one method that I found. This one is the one I'm showing because it jives with everything else I'm showing in this video. All right, so we're using the robust version of covariance estimates. And so here is my covariance matrix using robust calculations. When I get the eigenvalues, things are going to be a little bit different, but it's still the same flavor. Since I use a different method to calculate and estimate the variance, I'm going to get some different values, and that's okay. Use whichever one you feel is best for your project. And so now here I can get, I can use robust principal component analysis from the RR Cove package. That'll give me these results. Also, if I take my principal component analysis or my singular value decomposition, I can use either one of those to get low rank approximations of my data. Now, these approximations from a Euclidean geometry point of view are going to be the best approximation I can get for that rank. And so if I use one principal component or one singular value in there, I can get the best rank one approximation of my original data. If I use two principal components, I can get the best rank two approximation of my original data, and so on. And so here, just to show you what that looks like, is that I'm going to go through and I'm going to take the singular value decomposition and I'm going to build up a low rank approximation of the original data, or of the center and scale data, that is. Okay, so here I'm doing a low rank approximation of my original data, and I'm subtracting and taking the Frobenius norm. And so here, this is a rank one approximation, the best from Euclidean geometry point of view, the best rank one approximation I can get, the best rank two approximation, best rank three, and then, and then this one is rank four, which is the rank of my original data. And you can see that's not exactly perfect. That lack of perfection is due to rounding off inside the computer, inside the machine. All right, so we can also use biplots and visualizations to help us understand what's going on in our analysis. In a biplot, now this is kind of ugly. I'm going to show you a better one in a moment, but this is the default function. A biplot is going to go and it's going to plot each data points, principal component one and principal component two. That's the black letters. And then it's going to give arrows for each of the components to show the loadings, so we can understand how much does a particular column input into a component. And so we can see here, actually, you know what? I'm going to talk about that in a little bit. All right, so now here, this is using PR comp instead of print comp. And notice that things are reflected, but everything is relative to each other up to reflection in the same position. Now we can use a scree plot to evaluate how many components do I need to use. So there's a couple different ways to make a decision on this. First and foremost, I can say I want all the components that have a variance above a certain threshold. I can say I want a cumulative variance above 80%, 90%, something like that. Or I could use the standard that all components need a variance greater than or equal to 1. That's like a dynamics point of view. Or I can use a diminishing returns idea. Diminishing returns idea is that as I move to the right, I notice that I'm accounting for proportionally less of the data. And I'm getting diminishing returns as I move to the right. And so what we would want to do, we would want to, like, in our mind, put lines between the bar tops and find like where did we see like an elbow on there. And so here you might say we want two components, we might say three components. It's a subjective decision. Heck, you might even say one. Here it's not that clear on the data set. This one is using print comp. Notice that it actually has labels on the x-axis. PR comp does not have those labels. All right, so now I'm going to manually create a biplot to kind of show this a little bit better. Okay, so the states, what is going on is that after I do my principal component analysis, every point is going to have a PC1 coordinate, a PC2 coordinate, PC3 coordinate, a PC4 coordinate. The first two components are always the most important, or maybe not always, but more than likely the most important. All right, I'm going to plot each row's component one and component two. That's where I get the scatter plot from. And you can see just the location of each of these. Okay. And so now look at the arrows. The arrows correspond to the loadings. The loadings tell us how much does each column contribute to a component. Notice that the three crimes are pointed about equally much to the right. All right, so the horizontal component of the arrows are how much does a column contribute to the first component. The vertical component of the arrow is how much does the column contribute to the second component. All right, so we can see that the three crimes contribute about equally to component one. Now, when we look at component two, we see little input on each of the crimes, but urban population is off by itself. All right, so how I interpret this overall data is that component one gives us a measurement of total crime. All right. And component two really it's either a contrast between murder and urban population size, or it's really just a measurement of population. Depends on your interpretation of it. Now, something that I did to kind of help illuminate this is that you notice that urban population doesn't have much influence on component one. I went and I colored all of the points by their total crime per 100,000. So the original data is these three crimes per 100,000 population. Okay, if I add these all up, I'm going to say that that's crime per 100,000 because that's all I've got. So white collar crime, we're not worried about. Burglary, we're not worried about. But I'm just saying all our crime data put together. And so you can see that pretty well the colors correspond to the first component. Now, it's not 100% true. You can see that, that some green is getting to the farther left and some green is getting farther right, like Texas here compared to Illinois. But, it does a pretty good. Delaware is sticking out in a really weird spot. Now, my scree plot, this is the same scree plot as we saw before, but now I filled in the loadings. And so I made sure that in each bar, each column variable has a proportional to the absolute value of its loading is in the stack. And so here we can visually kind of see how much does each column contribute to a component, and we can see how much do I want each of these components. One thing I found, if something is so small that you can't plot things on it, it's usually so small you don't have to worry about it. So I definitely would not want to use component 4. Now, components 1, 2, and 3, where's the cutoff? You might say component 1 is enough. I might say component 1, 2. Somebody else might say we want components 1, 2, and 3 for a project. It depends on our project. Usually, for almost everything I do, I'm using 2 components. A lot of times I'm using scatter plots like we saw in the biplot to illuminate higher dimensional aspects of my data. Now, computing the pseudo inverse is super easy. I just switch the order of V and U. Notice I'm taking transpose on the right, but not on the left. And then I take the diagonal of 1 over the singular values. And then boom, when I multiply them together, you notice that I've got something that looks like a diagonal identity matrix. All right, also ggfortify gives us a quick way to get the scatter plot, and this will give us an easy way also to color the dots by columns of our data, but I didn't want to get into it. I just wanted the bare bones example to give you. And so here, if I just drop a principal component object into autoplot, you notice we get components 1, components 2, and they tell us how much does each component account for in terms of variance proportionately. All right. And Fortify is going to take our original data and put our components onto the data frame for us. That way we have everything in one nice spot. All right. Singular value decomposition is a fundamental tool for data decomposition and estimation. Principal component analysis and dimensionality reduction rely on SVD for extracting principal components. Singular value decomposition based estimation provides stable solutions for ill-conditioned systems, and covariance decomposition is useful in robust statistics in higher dimension analysis. All right, well, that's all I've got for you. Life is short. Do math.